This afternoon, I have the privilege of introducing Robert Lang, who's going to give a presentation about computational origami, and I hope you all enjoy it. Thank you.
All right, my title, From Flapping Birds to Space Telescopes. You're all probably sitting there saying, what could those possibly have to do with one another? But there is a connection. The connection happens through math as often as not through computer science. And I hope to make that connection by the end of this talk and maybe take us to a couple of interesting places along the way. But let me start with the easy part. What is this last word, origami? Well, most people have an idea of origami because you did it in school, kindergarten, or fourth grade. You folded cootie catchers and blow-up bunnies and flapping birds. And this is what most people think of when they hear the word origami. It's a Japanese word. It means paper folding. And it's an art form that goes back a very, very long time. In fact, it hadn't changed a whole lot. This is an image from 1797, woodcut. These women are playing with little strings of birds. And if you zoom in on one of these figures, it's this. This is the traditional Japanese crane, or tsuru. Every Japanese student learns how to fold this in kindergarten in Japan. And people have been making basically the same thing for over 200 years. This isn't the oldest known origami. There's this image is kind of interesting from 1734. It shows a crane, and there's a boat, and a little person, and a cube. And people fold these same things today. I'll bet half the people in this room have folded this little boat. So again, it's been around hundreds of years, people doing the same thing over and over. We don't even know where origami began. The oldest mention of origami comes in a book in 1680. They talk about these things called orasue and refer to these ocho and micho butterflies, which are these two shapes, which are butterflies, and they're clearly also folded paper. But we don't know when the art started. Now, the most common form of origami, and the rules you've probably heard about, is paper, an object made from a single uncut square of paper. And this restriction is actually rather modern. Old Japanese figures usually were uncut square, but often used cuts, often used multiple sheets. This was an example of if you take a sheet of paper and you cut slits into it, it's still one sheet, but it has cuts, but that's how you fold one of those strings of cranes, and people still fold the same kind of thing even today. So what makes something origami is that folding is the primary means of creating the shape. But folding only is still pretty restrictive. And so you would think that an art form that has such a restrictive set of rules, one sheet, just folding, and has been around for such a long time, that what would have happened is that long ago people would have figured out how to make everything possible that you could make in origami. And it would be a static art. And that might have been an accurate description up until the middle of the last century. And we can blame that on this man. Akira Yoshizawa, widely known as the father of modern origami, Japanese master, took up his country's folk art, origami, and began creating new figures. And he created hundreds and thousands of new figures, figures of great beauty and life. And his work inspired a worldwide interest and a renaissance in origami. But even more important than his own creations, he did something else. He created a language. He created this system of dashed lines and arrows and dotted lines that had a very specific meaning that allowed people to communicate how to fold an origami figure very simply and clearly from one to another. And that enabled a new mode of creation in the world of origami. Because one person could now learn from another, build off of what they learned from that other person, and then give back. And a third person could learn from them. And that ability to communicate and to share ideas and to build off each other's ideas led to an exponential growth in the world of origami that started in the middle of the last century and shows no sign of abating. And it has taken origami to a very new place from the simple flapping bird, cootie catcher, blow-up bunny. It's taken origami to something a little more like this. So this, too, is origami. One sheet, no cuts, folding only. But this isn't a flapping bird. It's a black forest cuckoo clock. It's my design from about 20 years ago. It's got leaves, and it's got a deer's head and a bird, and a door and pine cone weights and a pendulum, clock face, and it tells the correct time twice a day. But origami is not just about clocks. New modern origami figures show life and soft organic forms and details. We can throw in things like ears and horns and a beard, and he's even got cloven hooves on his feet. And modern origami can even create things that exist only in a mathematician's imagination, or perhaps nightmares. And so clocks and animals and Klein bottles and thousands of other origami shapes all come together and inspire a question. What changed? What caused this? And depending on who I'm talking to, I always give the same answer, but it's more provocative to some audiences than others, because what I say, what changed, is that mathematicians got a hold of origami. And my artist friends get a little hot under the collar at this, because they say, what do you mean? I'm not a mathematician, I'm an artist, and I've been creating origami figures. How can you say mathematicians got a hold of origami? And well, what I really mean is that both artists and mathematicians began applying mathematical principles to this art, learned what the underlying laws were, and then applied ramifications of those underlying laws. And that is what made all of the difference. The fields of math that touch origami are very diverse, and they range from fairly simple mathematical fields, plane geometry, trigonometry, all the way up to pretty advanced mathematics, graph theory, group theory, and, well, let's say the pinnacle of mathematics, computational geometry and complexity. Absolutely. I knew I'd find a receptive audience here for that thought. All these fields touch on origami. And I want to show, in the first part of my talk, what some of those connections are. So one of the areas in which math touches origami, contributes, is answering the question, what shapes and distances can you create by folding? Well, we all experienced this in high school, geometry, learned compass and straight edge constructions, but origami constructions turn out to be a little more general. The three famous problems of classic geometric constructions were trisecting the angle, doubling the cube, squaring the circle, but two of those, while all three were thought to be, are known to be impossible with compass and straight edge, two of them, the first two, are possible in origami. And it's not that complex. Here's how to trisect an angle. If you take an arbitrary angle, draw it in a square, then by making this sequence of folds, a line, divide in half, point to this line, point to that line, add a few more folds, unfold, and you'll find you get a geometrically exact trisection of the angle. It's not an approximation, it's an exact construction. You can work out the geometry to show that. Cube doubling, constructing two segments whose ratio is the cube root of 2. Once again, that's a very simple origami construction. This was discovered by Peter Messer, a Wisconsin mathematician, and he found if you take a square, go through this little sequence, bring this point to that line, this point up to this line, then once you've folded it, this point divides the edge in the ratio 1 to cube root of 2. So that's possible. You can do exact constructions in origami. You can also do approximate constructions for almost anything, and there's just a beautiful algorithm that makes use of the binary numbering system that some of you in here might be familiar with. And it's really easy. You take the number you want to construct and you just write it in binary. So 0.78, 25, 30 seconds, that's 0.11001. And the folding sequence is actually encoded in the binary description. You start at the least significant bit. And for every 1, you fold the top down. For every 0, you fold the bottom up. And you just go top down, bottom up, top down, 0. And the last fold you make divides the side in the desired ratio. And we can generalize those types of constructions. The general description would be starting with a square for a given point or line. How could I construct a folding sequence for that desired point or line to within a specified error? Now, crease patterns are made up of points and lines, but how do we make a point or a line? By folding. Points, there's really only one way. A point can only be defined as the intersection of two lines. So I could either have two creases defining a point, or a crease intersecting the edge. That's another type of line that defines a point. That's the only way to define a point. But what about defining lines by folding? Well, it turns out there were at least 6 ways of defining a line by folding. And for many years it was thought there were exactly 6. They were described by a fellow named Huzita, and so people call them the Huzita axioms. They're very straightforward. It said if I've got 2 points, that defines a line which goes through the 2 points. But with folding, I could also fold 1 point to the other, and that defines a line that runs between them. Or if I have 2 lines, I can fold 1 line onto the other, and that gives a bisector. And 3 other combinations, points and lines, point where the fold goes through a point, and finally 2 different points onto 2 different lines defines a line in a specific way. And for many years, people thought those were all the axioms there were. But in 2002, a Japanese mathematician named Hattori discovered a 7th axiom, which is shown here. If I have 2 lines and 1 point, I bring 1 point onto the line, the other line onto itself, and it makes a perpendicular. Then people found that actually Jacques Justin had found all 7 of them all the way back in 1989, but he had the bad habit of writing his papers in French. And people didn't read them, but now they know. And it has since been proven that there are only those 7 axioms. But with those axioms, you can solve a remarkable number of geometric problems. You can solve all quadratic equations with rational coefficients, all cubics, even all quartics. You can do angle trisection, cube doubling. In fact, you can construct every regular polygon whose number of sides is of this rather forbidding form where this is a prime number. Basically, that means between 1 or 2 and 20, everything except number 11. But that's simply folding 1 fold at a time. What if you could make 2 folds at a time? Well, recently we showed that you can quintisect an angle, divide it into fifths, and this shows the money step. If this is my angle in red, I make these preliminary folds and then bring all these points together on this fold and that fold, and it divides the angle 2/5 and 3/5, and that gives the quintisection. There are now known to be over 400 combinations of 2 folds that qualify as an axiom, so that have hardly been studied at all. So this is a wide open area of pure mathematical study in origami. But there's some practical use to this, because you can use these axioms to figure out how to make a specific fold. If you ask the question, what can you do with 1 fold at a time? With a single fold, you can't do much. If I just have a square, I can do diagonals, I can do horizontals, I can do verticals. This is all the things I can do with those 7 axioms. That's not much. But if I now start looking at sequences of folds, well, with 1 fold, I can make any of these lines. But with another fold, if I take any combination of these lines, I can make all those lines. And there's this very rapid geometric growth that within 6 folds, there's over 500,000 different points and 250,000 different lines within a square. So if someone says, I want to make this or that point or line, you merely need to go into this listing, a database of these, and find the line you're after and unwind backward the folds that it takes to get that line. Now that's a little tedious, so I wrote a program called Reference Finder that does this. And it builds that database and then spits out lines. And so if you type in, give me 1/3, Reference Finder gives you actually 4 different ways to construct it. What's remarkable is the very first way. You make a fold here, diagonal, then bring this corner up to that fold, and where it hits the edge is 1/3. That simple construction for a third was entirely unknown to origami. So simply by following the mathematical threads of origami, we can actually learn new facts that people haven't found. And while folding 1/3 sounds pretty trivial, as we'll see, using the same techniques, we can find some distinctly non-trivial constructions in origami as well. I'll mention as a side, my software Reference Finder is it runs on Mac, Linux, and Windows too. Both binary source codes available, and it's open source. So if anyone wants to write for the iPhone or Android or Web or Windows Mobile, it's out there. Have at it. But that's all how you'd find a single crease. But where do you decide what creases you want to begin with? Well, a crease pattern is a map of an origami figure. It's the plan. It's the blueprint for how do we fold. And we draw these crease patterns in a very simple schematic way using notation derived ultimately from Yoshizawa's work. There's two types of folds in origami. There's a valley fold shaped like a V, and we draw that as a dashed line. And then mountain folds shaped like a mountain, and we draw that with a solid line. And so this is a crease pattern. This is a plan for this three-dimensional shape, which is very simple. But every origami figure, no matter how complex, is nothing more than combinations of valleys and mountain folds. And they can all be described by a crease pattern. And so for something a little more complicated, we might have a few more folds in that crease pattern. This is a crease pattern for an origami figure, and I'll show the figure a little later in the talk. But it is still, even though it has hundreds of folds in it, it's still nothing more than mountains and valleys. And so what are the rules that govern one of these crease patterns? Can you draw any old pattern of lines, dashed and solid, and have it fold into an origami shape? Well, no. The answer is no. There's constraints. There's mathematical laws. And you might think the laws of origami are a thick book, that you have to study for years and years to learn all the laws. But they're not. They're surprisingly simple and surprisingly few. So simple and so few that we're going to go through them right now, and you're all going to go out of here and know all that there is to know about how to fold flat origami. So here we go. What's the first rule? Well, it is that every origami crease pattern has to have a property called two-colorability. Basically, that if I color all the regions so that no two colors border a common line, I only need two colors to do that. You might know that any general planar map might need 3 or 4 colors, not more than 4. But origami patterns must have the special property that they are two-colorable. So that's law number 1. Law number 2 relates to mountains and valleys, how many there are at a vertex. And it says if I go to any vertex and I count up the number of mountain folds, here I've got 1, 2, 3, 4, and I count up the number of valley folds, 1, 2, the difference between the numbers of mountains and the number of valleys is plus or minus 2. There's 2 more or 2 less. So here I've got 4 and 2. Here I've got 1 and 3. And if you look at every vertex in the interior of this pattern, that law is satisfied. And it must be satisfied for a valid flat-folded shape. If instead of looking at fold directions, we look at the angles between the folds, the third law applies. It says if I number the angles around any vertex, 1, 2, 3, 4, 5, 6, then the sum of all the odd-numbered angles has to add up to 180 degrees, to a straight line. And the sum of all the even-numbered angles, of course, also then must add up to 180 degrees. And that, too, must be satisfied at every vertex. And the last set of rules was formulated by Jacques Justin, he of the 7 axioms, and they relate to what's allowed in terms of stacking the layers up. And basically, they boil down to saying the paper can't intersect itself. So that if you have a fold and a sheet that overlap, well, I could put the fold above the sheet, or I could put both layers of the fold below the sheet, but I can't put one layer above or one layer below, because then the sheet would have to intersect the fold. If I have 2 folds side by side, they could be one above the other, or one wrapped around the other, but you couldn't have the layers alternate because, again, the paper would penetrate. And so that condition needs to be satisfied. And that's it. That's all the rules of flat foldable origami. If you come up with a pattern that satisfies those rules, it's guaranteed to fold flat. But the question arises, how hard is it to do that? Well, it turns out that satisfying two-colorability is easy. Actually, really easy. It's very easy to draw a map that's two-colorable. Satisfying the angle condition, that's also pretty easy. Satisfying alternate angles, that's easy. But this layer ordering thing turns out to be kind of hard. How hard? Well, let's take a little detour. Let's find out how hard. Let's look at side-by-side folds. If I have a mountain fold next to a valley fold, then here's what the side view of the paper looks like. It makes a zigzag. And there's 2 possible ways I can have those mountain and valley folds. I could put the mountain fold on the left, or I could put it on the right and have the opposite zigzag. And those are the only 2 ways of assigning folds to that pair of lines. So let's give names to those 2 situations. The valley fold's on the right, we're going to call it true. that the valley folds on the left, we're going to call it false. Now, what happens when some of these trues and falses come together? Well, if 3 of them come together at a triangle, it turns out all the angles can be satisfied, but layer ordering dictates that in the middle, you can't have all 3 of them be true. Basically, if I have 3 true pleats hitting, then all 3 layers want to be on the top, and you can't have all 3 on the top. So the only way to assign mountains and valleys to this crease pattern and make it work out is to have either 2 trues and a false, or 2 falses and a true. And so we'll call that crease pattern, we'll call it a not all equal, because it enforces that all the pleats can't have the same assignment. Well, in 1996, 2 researchers at Xerox PARC developed a whole series of folding gadgets that could create not all equal clauses on these true-false pleats. They could create reflectors and crossovers and splitters that allowed you to encode any logic problem of a type called not all equal 3-sat in a crease pattern. So any not all equal 3-sat logic problem had an origami equivalent. Solution to one gave the solution to the other, vice versa. And that was the interesting result, because you see, not all equal 3-sat is a special problem. It's NP complete. And what they proved was that the problem of assigning creases to an arbitrary origami question was also an NP complete problem, and therefore gave an efficient solution. If an efficient solution existed for the origami problem, it would give an efficient solution to a wide range of other very hard problems. So in fact, they proved that origami is hard, which is something that we origami people knew all along. But what it showed was that origami problems relate to some of the most fundamental problems in computer science and mathematics today. As probably many of you know, anyone who could find an efficient solution to the NP-complete problem would probably be a billionaire because of all of the practical applications. And if they could prove there was no efficient solution, then they'd only be a millionaire because they'd win $1 million prize from the Clay Mathematics Institute. The cool thing that Byrne and Hayes also showed is even if you have the complete crease assignment, you know every fold, just determining which layer's on top was also an incomplete problem. So flat foldability requires solving 3 easy problems and 1 hard one, the just stand conditions, and that's all we need. Fortunately, the hardest problems, the ones that stress the algorithm, rarely arise in real origami situations. Most of the problems are in fact solvable, and so we can use these laws to design origami. And the question that comes up, is it useful, or is this just spinning our wheels with math and computer science? Well, these flat foldability rules are very abstract. They're just math. But from those rules, we can construct applications. We can pattern matching rules for building real origami figures. And that's an application. That lets us construct objects of great beauty, art, and we can use these same rules to solve real-world technological problems and maybe even make a little money along the way. So let me show how some of that might happen. I'm going to start with the area of folding called textures. Just patterns, repeated patterns, periodic patterns, tessellations. If I take a sheet of paper and I put a bunch of vertical folds in it and a bunch of horizontal folds in it, I get a little pattern of squares. And you go, big deal, little pattern of squares. That's boring. But if I rotate it to a diamond, then I say, well, now I've got a little pattern of diamonds. But it's still pretty boring. All by itself, no one's interested in that. But what we can do now is to take repeating patterns like that, and using these laws, we can splice this crease pattern into another crease pattern, say a crease pattern like this that folds into this fairly simple fish. And by putting the pattern together with the creases, we can then create an object of considerable beauty. This koi is still one uncut square of paper with about 400 scales. It takes about 8 hours to fold. So there's only one of them. If we don't want to fold 400 scales, well, we can do just a few, but still use that technique to get plates on this turtle, for example, and the feet. Or if we're feeling kind of frisky, rattlesnake this one has about 1,000 scales on it. And after I folded that, I swore I would never do another 1,000 scale rattlesnake. So this has 1,500. But I probably won't do any more of them for a while. It does, however, let us create textures on demand. When someone asks for or requires a structure that has a periodic pattern, we know how to create that periodic pattern and insert it into a crease pattern. I want to show another example. Here's a crease pattern for a commission I had about a week to design, fold, and have it ready for my client for photography. Here's the crease pattern, still nothing more than mountains and valleys and a big periodic pattern. Here's how it went together. We start with a square of paper. First transfer the crease pattern to the square, and then start folding. A lot of these things you have to bring all the folds together at once. There's no first fold, it just all has to happen together. The intricate pattern takes a little fine work, but when it's done, 50 stars and 13 stripes. Gee, thank you. Surprisingly, though, the greatest successes of math and origami came not in the area of patterns, repeating patterns, but in the area of representational origami, design, things with arms and legs and wings and antenna and so forth. And that came about because we can write down an equation for the design of an origami figure, and here it is. You start with an idea, you combine it with a square, and you get a folded subject. There it is. Now, of course, what really matters is what goes on here? What am I implying by these symbols? And you might be sitting there wondering, can you be that specific? I mean, this is a beetle. This is a stag beetle. It's got 6 legs. It's got a head, thorax, abdomen. It's got antenna. It's got jaws. The jaws have 2 little pincers on the ends and 1 in the middle. I mean, can you really be that specific about what you want and fold it? And yeah, you really can. So how do we do it? Well, let me take that equation and let me stretch it out. Let me break it down into some steps. And let me start at the end and work backwards. So I want to end with a folded something or other. Well, to get this folded beetle, I need a shape that has paper, a little bit of paper here for the leg, and a little bit of paper for each antenna, and a little bit of paper for each jaw. So what I need is a shape that has a flap of paper in the right place, of the right length, for all the features. And we call that the base. Now, how would I describe a base? Well, I want to know how many flaps there are, how long they are, how they're connected to one another. The simplest description that conveys that information is a stick figure or a tree graph. And so I draw a tree graph. There's my leg, there's an antenna, there's a jaw. And the tree graph is just a schematic representation of the original subject I've got. Now, how do I go forward? Well, going from the subject to the stick figure, that's really easy. Because even a kid can draw a stick figure. That's the first stage of drawing that we all do. We think naturally in terms of that form. And if you had the base, going to the final form, well, maybe that's not quite as easy, but maybe you'll grant me that if you had that shape, you could take the flap for the leg and you fold it in a zigzag, and that would make a zigzaggy leg, and you'd take the antenna and you'd crunch it down to be long and skinny and shaped like an antenna. So you grant me that you could probably go from here to there. But going from here to the base, that's the hard step. That, however, is the step that mathematics can help with. Mathematics can get us over the hard step and let us complete this full sequence. So there it is. We start with a stick figure, and we want a base that has flaps in the same arrangement as the stick figure. So a base is nothing more than a bunch of flaps. The question of designing base is simply the question, how do you make a bunch of flaps? Well, that's too hard. Let's start with the easiest possible version of that problem. How do I make a single flap? Okay, so I hand paper out to you and I say, fold me a flap, a long skinny bit of paper. And you probably do something about like this. You take the square, you fold it in half and in half again till it gets kind of long and skinny. And you say to me, how long should this be? And I say, make the flap about this long. And you go, okay, I'll put a little fold here and so that this is my flap. And this is just all leftover stuff. So here's my flap. There's the boundary, above it is flat, below it is leftover. Now let's unfold it and take a look at the crease pattern. Well, the creases of the boundary form this little arc. There's all my long folds. All the paper on this side of the arc is flap, and everything over here is leftover. So that's our first data point. And I say, well, make the flap skinnier. Well, that's easy. You just fold it in half again, make it, or 2 or 3 times to make it skinnier. And when you unfold it, you'd find that the boundary is getting smoother and smoother. And so if I take the limit of an infinitely thin flap, the boundary becomes a quarter circle, and the minimum amount of paper of all of these flaps is the skinniest one. It's a quarter circle of paper. So a single flap requires a quarter circle of paper. And the radius of that circle is just the length of the flap. That's not the only way to make a flap, though. That flap came from the corner of the paper. What if it comes from the middle of the edge? Well, you go through the same process, and you'd find it comes from a half circle. And I said, what if that flap comes from somewhere in the middle? You go through the same process, you'd find it comes from a full circle. So no matter where the flap comes from, it uses some part of a circle. And in fact, we can unify this idea by recognizing, actually, it's always a circle. We just allow the circle to overlap and fall partly outside of the square. So a corner flap is a full circle that overlaps the corner. An edge flap is a full circle overlaps the middle. A middle flap is a full circle in the middle. So no matter how you make a flap, it always takes up a circular region of paper. So now we've beaten the single flap to death, but we're ready to move on to the tougher problem. What do I do if I want to make something more complicated? What do I need to make a bunch of flaps? I see someone has a guess. You can move the circle to other parts of the paper, and it can be off circle or off center. And that arises, in fact, when we address something with more than one flap. The way you design a shape that has more than one flap is you use more than one circle. And this was the great insight of origami. That if I wanted to make a spider with 8 legs, it had to come from a base with 8 flaps. I could find the allocation of paper simply by finding a packing of 8 circles. So some in the corners, some on the edges, some in the middle, some a little off center. As long as the circles are at least partially in the square, their centers have to be in the square, and they don't overlap, that gives a valid distribution of paper that gives a base that folds into that shape. Now, why did I say they can't overlap? Well, what if they did? Well, then the paper in the overlapping region would have to be in 2 different flaps at the same time. And that's not physically possible. So the rules are simply pack circles, don't let them overlap. That gives the allocation of paper, but that doesn't give the creases. So the next step is, where do the folds go? Well, we found that whenever circles touch, there are always folds between their centers, but there had to be many more folds in here. So how do we fill in these polygons with the right folds? Well, each polygon in one of these patterns turns out to give a little piece of the crease pattern. A triangle gives a 3-legged piece of the crease pattern. A quadrilateral gives a 4-legged piece of the crease pattern. So what we really needed was to find the folds that turned polygons into little pieces of the crease pattern. And those patterns of folds we called molecules. And the simplest molecule is very easy. For any triangle, if you put folds at angle bisectors coming in and draw perpendiculars to each face, then you get a little 3-legged shape, and that is a 3-legged piece of the stick figure. And that works for every triangle. Quadrilaterals were a little tougher. Husimi, Kawasaki, Mayakawa, and myself all found patterns that turned any quadrilateral into one of the 2 possible 4-sided stick figures. And eventually I found a pattern called the universal molecule that actually worked for any stick figure, no matter how complex. And those gave the creases for any polygon that we could put them all together and create the crease pattern for the base. And this led to a very systematic way of creating an origami shape. You start with the shape you want, you find a packing of circles, you decorate it, with these molecules. That gives what might look like a very complicated, forbidding crease pattern. But this crease pattern, constructed according to these rules, is guaranteed to fold into a base. And the base is guaranteed to have the right number, length, and connectedness of flaps to be turned into the final shape. And this ability led to a revolution in the world of origami, and it led to a new era in origami design that I call the era of intelligent design. Because, you see, if you wanted to make this shape, you couldn't find it by trial and error. You would play around with the paper for forever, and you'd never get this particular combination of a bull's body, wings, head, and so forth. By the way, this is an Assyrian god who's in the Asian Art Museum at the University of Chicago. But using these techniques, you could construct exactly this or whatever else you wanted. And this system of design, called the circle river method of design, was so powerful that people could run right out and with nothing more than a pencil and paper design extremely complicated origami figures. But it's so systematic, it's so step by step, so algorithmic that you can now ask the question, can I automate it? Could I do more if I had more than a pencil and paper? What if I had a computer? So this problem can be computerized. And I wrote a program a while ago that did that. Now, to solve it on a computer, you need a formal algebraic description of the problem. And this is the algebraic description of that same problem of the circle packing. It's simply optimize a variable subject to a bunch of algebraic inequality and some equality constraints. Linear objective, it's a non-convex feasible region. This is a nonlinear constrained optimization, the type that people have been solving for decades in computer science. And by building off of what they've done, then we can solve for origami crease patterns that are impervious to solution by hand. So for example, here's a stick figure. And my program, you can draw this stick figure. It's got legs and a body, front legs and neck, ears, head, antlers. That turns out to be equivalent to about 200 equations. That's child's play for modern optimization software. And so if you draw this stick figure and assign all the lengths and plug it in and say, go calculate the crease pattern, you get the crease pattern that folds into that shape. There it is. It's obvious, right? Well, maybe not. Let me show a few features, though. You can see the circles. This is a circle for a tail and a back leg. That's a front leg. That's a front leg. That's a nose. One ear's over here. One ear's way over there. And all this stuff up there is the antlers. Still not convinced. Understandably. But if you take this crease pattern, you fold it up, you will get a base. It will have flaps in all the right place. You can do some more shaping, and you can get that deer, an eastern white-tailed deer. And you can be that specific. Eastern white-tailed deer has a certain branching pattern to the antlers, but if you're in California and you want a mule deer, you change your stick figure, you change your circle packing, recalculate, and you can fold a mule deer. Or if you want bigger antlers, then you can do an elk, which has yet a different branching pattern. And if we have anyone from Maine or Canada here, this one's for you. So this led to a new approach to origami design. But it also led to conflict. It led to something called the bug wars. Here's what happened in the bug wars. Back in the 1970s, people thought insects were just impossible. They had so many legs and wings, you couldn't do insects from a single uncut square of paper. And you can even find books that would say that. But in the 80s, people started figuring out how to do insects. In the 90s, these circle packing techniques came along, and people were battling over specific species of bug. And here's how it would go. One person would fold their spider, say 8 legs. Here's my spider. It's got 8 legs. It's got pedipalps. It's even got chelicerae. What do you think of my spider? Pretty good, eh? Next person say, yeah, your spider's okay, but my dragonfly has 6 legs and 4 wings. 6 plus 4 equals 10. Your spider only has 8 legs. Mine's got 10 appendages, so mine's better than yours. Next guy would say, well, you know, the legs on that dragonfly look pretty plain. In fact, you really need to put the claws on if you want to get everything right. And my samurai helmet beetle has claws. And it's also got a horn on the thorax and a big horn on the head. So that's 2 big horns as well. And next person say, well, 2 horns is nice, but 5 is better. And people would actually pour through entomology journals looking for beetles that had more and more horns to try to one-up one another. And you'd go in different directions. Say, let's do something that has long, skinny legs, like a praying mantis. 6 legs, they're really long and skinny, plus the head and the antenna. How are you going to top a praying mantis from a single uncut square? And there's really only one way to do that. 2 praying mantises from a single uncut square. And I call this one snack time because she is just about to start nibbling on him. And this, by the way, this is what that crease pattern was that I showed early in the talk that had all those creases. But people had to move out of insects and to other arthropods to get enough challenge. So, centipedes. And person fold a centipede, the next guy'd come along and go, count the number of legs and say, okay, I'll double you. We could take it in different directions. Try for authenticity in a different way. This is a full tick. He's already eaten. But we could also move towards a little closer to actual size if we want. And similarly, this leafhopper is also actual size. One of the interesting developments from these is that their crease patterns turn out to be rather pretty all on their own. So for this flying katydid, its crease pattern is kind of a neat pattern, and I've had people just want to use these as decorations. A recent commission is this Camel Spider. Camel Spider's, it's not a true spider, but it's this nasty arachnid that's got 4 jaws. It looks like an alien villain sort of thing. Pretty ugly looking, but its crease pattern is really pretty. I kind of like it. And this battle is going on. The latest salvo is a friend of mine emailed me his praying mantis. This is by Sipo Mabona from a folder from Switzerland. And here's his praying mantis, which I just think is stunning. If you look close, you'll notice it's got mouth parts. Really, really detailed. But we could do more than just create insects, because for every one of these designs, underneath it, there's a stick figure. And certain types of stick figures have a mathematical significance. The conditions on the stick figures for star trees, where all of the sticks come from a single point, turn out to be very similar to a straight circle packing. That for this tree, 5 different stars, that's a packing of 5 different circles. And so for every circle packing that's out there, there's an origami base, and vice versa. And although the origami problem, the circles can overlap, if the circles are all equal size, that turns out to be the same as a packing problem where the circles fall entirely inside a box. And so one can use the existing literature on circle packings to discover origami figures. And that lets us make use of a valuable tool for productivity in the sciences. The secret to productivity in the sciences is letting dead people do your work for you. And in this case, building off of what dead people have done, or even live people, what others have done. If you can adopt their solutions to math problems, turn your problem into one they've already solved, you can accomplish a lot. And so the most efficient origami bases turn out to come from these disk packings. And so people have studied disk packings. Here's packings from 1 to 9 circles, and just by drawing the lines over them, that gives you an origami base with 1 to 9 flaps. The best 10-circle packing, actually, the record changed hands 5 times over 25 years. For every one of them, there's an origami base. And this origami insight even lets us solve some problems that were unknown or unsolved in mathematics for a while. Famous problem called the Margulis napkin problem. It's a folding problem. Margulis napkin problem asks one to prove that it's impossible to fold a unit square to form a flat shape whose perimeter is greater than 4. Now, unit square has a perimeter of 4. And so what this problem says is prove that no matter how you fold it, you can't make the perimeter larger once it's flat. It's a very tough thing to prove. One of the reasons it's tough to prove is that it's not true. And a counterexample, the first counterexample actually came from origami. Here is a shape that has a perimeter of 4.1. If I take I fold this shape. This is called a bird base. It's the basis of that 200-year-old crane, and you just add a few more modern folds called sync folds, and you make this little human-shaped figure. And if you carefully do the bookkeeping of all the perimeter, turns out its perimeter is 4.12. So we know that conjecture is false. But what's the maximum? I mean, here we did a ton of folding, and we got from 4 up to 4.12. So, can you go higher? Maybe 4.3, 4.5. What is the upper limit? Well, we can solve this with an origami base, because one of these little structures is just a tree, a stick figure. And so stick figures come from circle packings. Let's look at a stick figure made up from circle packing. So here's my little tiny star tree. It's made up of a set of circles, and we'd find the length of the circles goes as 1 over m. The number of circles goes as m squared, which means the perimeter has an m number of circles squared upstairs, single m downstairs. Perimeter is unbounded. Turns out you can fold a shape with an arbitrarily large perimeter from an arbitrarily small sheet of paper, as long as it is that special zero thickness paper that mathematicians like to use. But this came from origami. And so we can use these techniques to solve math problems, but we can also use them to create beautiful works of art. Not just insects, but animals, for example. We can put claws on a grizzly bear. We can put toes and eyes on a tree frog. We can make human figures. We can make figures that have more than one component from a single sheet of paper. So this man playing a guitar, that's from a single sheet. And the man playing a bass, all of that's from a single sheet. And you might, be sitting there and think, well, a guitar and a bass are pretty simple instruments. Could you do a more complicated instrument from a single sheet? And yeah, you can. So this lets us create almost anything from origami. And origami has turned out to have applications in and be used in graphics and advertising and print ads. And all this is possible because we can create origami figures on demand. And as an example of this, I want to show a commercial that I worked on a couple years ago. And I'll start it in just a second. I'm just going to let it play, but before you start, know that everything you see, except the car, is origami.
その伝説はよく知られている。それは山を支配する。それは植物を支配する。それは風を支配する。それは都市を支配する。それはエンデバと呼ばれている。
The 2006 Mitsubishi Endeavor, with a powerful 3.8-liter V6 and available all-wheel drive, a mythic combination of beauty and beast. Mitsubishi, driven to thrill.
So a lot of computer modeling made things move, but everything that moved was a folded sheet of paper. And I'll just show one still photo as we were putting the sets together for the Victorian houses. My partner for this project was Linda Tomoko Mihara, very talented origami artist from San Francisco. So I mentioned I wrote this software that one can use to design. It's called Tree Maker. And there's this great ethic in origami of sharing and giving away your secrets and telling how things are done. And so the algorithms in Tree Maker are described both in technical terms in a paper and in lay terms in a book I wrote. And the software is open source, runs on Mac, Linux, and Windows, and you can download it from my website and do what you want with it. And Tree Maker was the first origami design software, but it's been joined by quite a bit of other software. By folks named Tomohiro Tachi, a brilliant Japanese graduate student. Jun Matani has developed software for designing folds. And I just want to show one example from this, what I think is the coolest origami software in the world. Tree Maker takes a stick figure and gives you the crease pattern that folds into a shape conformal to the stick. Tachi wrote a program, Origamizer, that takes an arbitrary surface and gives you the crease pattern conformal to that surface. And so, as one example, here's what his program does to the Utah teapot. Over there, that's the crease pattern. It's a little faint, but it's a very dense network of creases. And if you fold it, this is what you get. That's not a rendering. That's the physical folded paper object, according to that crease pattern. Alex Bateman, gene sequencer in England, has written this program that does periodic analysis, periodic patterns. Here's what his program Tess creates, and these are some of the folded examples based on the design. And that leads me into my next area, which is perhaps the hottest area right now of origami, geometric origami. Flat patterns called tessellations, look like tilings, division of the plane, 3D tessellations, curved surfaces, and more. This is the cutting edge, so to speak, of origami today. And I just show a few simple examples. Here's a spiral tessellation, an egg-shaped tessellation. These are patterns that don't look like something. They're beautiful just in the patterns of the folded edges. This is a very recent design of mine. And it looks like it has to be made of strips of paper going under and over, but it's still just one uncut sheet of paper folded to look like that. Linda Mihara has used tessellations to create clothing. Here's a dress. She says it's a size 0 if anyone out there wants to try it on. Shoes to go with it. And this field has its roots not so much in the traditional Japanese art of origami, but actually in computer science. Ron Resch, a computer scientist, back in the 1960s, designed and patented periodic folded paper forms like this one and created shapes, periodic shapes, domes, spirals, beautiful curved structures. It was quite the pioneer. One of his proteges was a computer scientist named David Huffman, who developed a lot of the mathematics of origami. Now, Huffman is not known in the origami world, but he's reasonably well known in the computer science world because he invented a thing called Huffman codes. He also invented a lot of the mathematics of origami that allowed you to do faceted shapes, curved shapes, and even to design the crease pattern that would cause a strip of paper to spontaneously tie itself into a knot. And you can even specify the type of knot, a trefoil or a torus knot or whatever knot you like. And he created figures that open and close. This pattern has, if you pull on it, it spirals as it opens up. And that's beautiful and interesting, but it might even be useful. And in fact, that pattern and others like it are. Origami has turned out to have applications in the real world. Applications in space, in automotive, in medicine, in consumer electronics, and many other fields. And I want to show some examples now of real-world applications of folding and origami. This is a folding pattern that you can make very easily. Zigzag valley folds, zigzag mountain folds, and connect with alternating mountains and valleys. It's called the Miura Ori because it was studied by this man, Koryo Miura, who realized this pattern would work really well for an expandable structure for space. And it was adopted as the basis of this solar array for a Japanese mission that flew in 1995. We in the U.S. fold things and put them in space. There's this telescope under construction now, the James Webb Space Telescope. And it's got 2 vertical folds so that the sides of the telescope fold in to make this little compact package. Why does it need to do that? Well, it needs to get to space in a rocket. And rockets are not all that roomy, so the thing needs to be made small for the journey and then open up large and flat at the destination. And whenever you have those 2 requirements, big and flat at the destination, small for the journey, folding and origami can provide a solution. The James Webb Space Telescope folks didn't need any origami people to tell them how to put 2 folds into a lens. That was pretty straightforward. But a more ambitious team at Lawrence Livermore Lab had set their sights a little larger. They were designing a lens that would be 100-meter diameter to go up in space. About 2 kilometers away, you put the eyepiece, the camera, and then you've got this lens out there. So that's a lens the size of a football field in space. About the only place you could put it. But there's a lot of space in space. Problem is, how do you get it there? Once again, it's got to go up in a rocket, so you have to get it down to no larger than about 3 meters. And that calls for some pattern, but a much more complex folding pattern than 2 folds of the Webb telescope. So here's one possible solution, and here's how you'd put folds into a glass lens. You cut up the plates and you put flexure hinges between them, but you can't use pie slices for 100 meters because it would still be 50 meters long this way. So I got involved with them, and we worked on a bunch of different folding patterns, including some that wind up in a tight spiral. There's a crease pattern, partial crease pattern up there, very similar to that first Huffman pattern, but we settled on this one, which we called the umbrella. It's a ring, and with this pattern of creases, the ring folds down into a little cylinder. And one of the nice aspects of this pattern is you can keep adding more rings, and they all fold down conformal to the same cylinder. It's also manufacturable because you can make the whole thing from just 3 different shapes: triangles, rectangles, half triangles. And so they adopted that for their first prototype. Here was an opaque structure used just to test the folding, and that's the first generation lens, a 5-meter lens. This is terrestrial only. It was used for ground testing, but it's about twice the size of the Hubble Space Telescope, and yet folds down into about 1.5 meter bundle. Japanese have flown solar sails that start out folded and unfold as they unfurl. You can see fold lines as this photograph of the sail as it unfurls from its rocket. There's also an amazing project of the Japanese Space Agency to fly paper airplanes down from space. And that sounds pretty crazy and pretty unbelievable, but this is one of the planes that they've tested. This is in a wind tunnel, and this plane has already survived Mach 7, 400 degree Fahrenheit. So it might just make it. A Hughes Research Labs researcher named John Myers showed that origami simulated the bouncing of light pretty effectively. And that was sort of a toy example. But then about 10 years ago, one of the engineers who worked for me at my laser company, Mats Hagberg, realized that if we took a rectangular laser cavity and put 2 folds into it, then the light would bounce around between the folds and would actually get cleaned up as it bounced between the folds, giving a higher power, brighter beam. And these things then turn out to be used in surgery and photodynamic therapy and metabolism studies. And one of these bouncing light lasers is shown here, and what it's doing is it's blasting a hole through some razor blade, which may not be much, but the laser itself is about the size of a fingernail clipping. People find folding in the most unlikely places. Biologists look at cell membranes, and they want to study the thermodynamics. And this is a computer simulation of a cell membrane. If you zoom in, it starts to look on the most microscopic scales like a grid of folded triangles, where the vertices are the atoms. Folds happen along atomic bonds. And so at the smallest scale, this membrane is nothing more than a grid of folded triangles. And people are interested in the thermodynamics of it, the entropy of this system. Well, the entropy comes from the number of different ways of folding the surface, so this thermodynamic problem really is a folding problem. How many ways are there per unit area of folding a triangular grid? And so, people study the number of ways of folding a triangular grid to get insight into this biological problem of the behavior of cell membranes. And so they try to count the ways using temporally Lieb algebras and complex things. On the other hand, origami artists just simply fold triangular grids in interesting ways. This is work by Joel Cooper, a Kansas origami artist. People also look at folding on the very smallest scales in proteins. You see these cartoons that represent proteins. Of course, they don't actually look like this, but they're represented by strips because the laws of folding of these strips are the laws that govern the shape of this protein. And the shape governs its activity. So if you know how to fold a protein molecule on large scale or very small scale, you can predict its behavior, and perhaps you can find solutions to diseases that arise when proteins misfold, fold in the wrong direction. That problem I talked about, small for the journey, large at the destination, comes up a lot in space, but it even comes up in the human body. This is a stent. It's an implant, goes inside a blocked artery, holds it open. It's a little tube. But to get it to the blockage, you have to make it smaller. And so this tube needs to collapse down to a small bundle. Zhang Yu, professor at Oxford University, realized that using an origami pattern, you can see folds here, and these folds run this whole length of the tube, that origami pattern provides a very effective way of collapsing this stent down into a small bundle. And this device is now in medical test, in FDA testing. A company called Paracore Medical makes a heart implant that is injected between the ribs. It's a bag that wraps around the heart but that bag has to fit into a small tube, small enough to get between the ribs so you don't have to crack open the chest and do open heart surgery to install it. Once again, folding provides the solution. That bag is folded down into the tube in a special way so that it does not snag on the way out. Again, small for the journey, large for the destination. The most outrageous or surprising example has turned out to come in the area of airbags. Now, airbag designers have this problem. Airbag needs to work for big people and little people, car going fast, car going slow, front impact, side impact, person sitting close to the wheel, far away. It's got to work under all those conditions. And you really only have two ways of ensuring that it does. You can either crash a lot of cars under different conditions or do simulation. Of course, they'd much rather do simulation. But the simulators had a problem. Designers designed the airbag fully inflated. But the simulation needs to start with a flattened airbag. And specifically, it needed to know the positions of the creases in order to create the mesh for the finite element analysis. So they needed to know what are the creases that flatten an arbitrary polyhedron. Turns out, the creases you need are the molecule crease patterns. Those patterns I talked about earlier that we came up with when we were designing insects. So by using the molecule specific to this polygon, as if it had appeared in a crease pattern, airbag simulators could flatten the airbag in the simulation and then run the FEA analysis. And so there's our origami creases. Add your mesh, do your simulation, boom, the airbag inflates, and hopefully it does its job. There's an amazing number of connections now between origami, math, and science, and solutions, and cross-fertilization. If I may be forgiven, a small plug. A bunch of these are described in a book that I edited, but 46 different authors wrote articles about these connections on origami, math, science, education. It's titled Origami 4, published by A.K. Peters. You can learn a little more information about this at my website. And there is going to be a new Origami Math, Science, and Education Conference in Singapore it's now in July 2010. And if you Google for 5OSME, 5OSME, you can find out lots more information. But I don't want to stop there with shameless plugs for books and things. I want to stop with a question. Where did all this come from? You know, where do these solutions arise? Well, this heart stent of Zhang Yu, that pattern comes from the little blow-up balloon called the water bomb. And the reason people knew that it would work for a heart stent was because people had analyzed what happens when you take that crease pattern and you make arrays of them. How does it move? And the airbag flattening algorithm, how did they solve that problem? That came from the molecules that insect origami designers came up with to design origami insects and beetles with lots of horns. And this sort of thing happens all the time in the sciences, art, and especially mathematics. That problems you solve for their own aesthetic value very often turn out down the road to have real practical applications. In the case of some of these origami problems, it might even save a life. Thanks very much. We have a question. Are there investigations of origami folding in the hyperbolic plane? The answer is yes, and I can't say more because I'm sworn to secrecy until the paper comes out. Yes?
Early on you mentioned that the restriction against cutting was water restriction. What difference does that make in what is possible to fix?
Turns out it makes very little difference in what's possible mathematically, because it's been proven you can create any flat shape, any 3D shape, and any two-color pattern. If you have given enough paper, you can do it with one sheet, no cuts. From an artistic sense limitation, it makes a big difference because you can't really fold things that have exponential numbers of layers. But because we've discovered so much is possible with the restriction of no cuts, most origami artists voluntarily accept the restriction of not allowing cutting. Because once you start cutting, where would you draw the line? You could then just cut out most of a silhouette. The place where cutting still shows up is in those strings of cranes, where you cut slits in the paper to make connected cranes. And that remains popular.
Early on in your presentation, you had edge weights on your graphs. What were those?
Oh, so the question was the edge weights on the graphs. The edge weights on the stick figures on the tree graphs are the desired lengths of the corresponding flap. Yep.
You were talking about the arbitrary surfaces and how they made the U5T5. Could you use origami for like rapid prototyping, for instance?
Yeah, the question is, can you use origami for rapid prototyping? The answer is yes. However, the actual process of folding those crease patterns can take a really long time. So I wouldn't call it rapid prototyping because of that aspect of it. But yeah, it's absolutely possible. And in fact, not just for prototyping, for short-run manufacturing, there are companies and outfits who are using origami to make parts to avoid creating dies for stamping large numbers of parts. Die's $250,000, but if you can cut it and fold it from sheet stock, that's much cheaper. Yep.
What kind of options exist for robotic, automated folding of metal, for example, something you can't do by hand?
Well, there have long been special purpose robots for folding specific structures. Those are machines, for example, that assemble cardboard boxes, fold them, but they're special purpose. They fold one or a small number of types of box. There has been study on trying to build general purpose folding robots. The most advanced I know of was done by a professor at Dartmouth named Devin Balcom. But his robot is general purpose, but could only do the very simplest of patterns. What is a little more advanced now is people are working on making smart materials that, and Eric Demain and his coworkers at MIT are doing this work where you build actuators into a kind of a universal crease pattern so that you can make the material fold itself into one of several desired shapes. Yep.
Those micro ones, the ones that were smaller than a coin, the life-size bugs.
Yeah.
How are those folded? And then also, how much is the shrink from the size of the paper down to some of those more complicated things?
Okay, I'll answer the second part first. The shrinkage is surprisingly not as much as you might think. Typically, the finished size will be between 1/4 to half the size of the original sheet, which is, you'd think it'd be smaller, but though these design techniques turn out to be very efficient in the use of paper. For the small bugs that I showed in the pictures, I folded those with tweezers and my hands. And years ago, when I had when I was doing semiconductor work, I would fold tiny things under a stereo microscope with tweezers. But the record for the smallest fold is about an order of magnitude below what I can do and showed. The smallest crane that's been folded, I think, was from a 250 micron sheet of paper. And there's an SEM photograph of it somewhere on the web to prove the crane is sitting on the point of a pin, and and the pin is like this huge rounded mountain. It's quite impressive. Yes.
Are there studies on like folding into in dimensions?
I'm sorry. Say
like
that.
Folding into in dimensions instead of just three-dimensional.
Yeah. The question is, are there studies? Have people looked at folding in higher dimensions? And various mathematicians have. One of the folks I mentioned who does geometric constructions, Professor Robert Geretschlager at Kepler, BRG Kepler in Graz, Austria, has looked at folding in higher dimensions, typically moving into the fourth dimension. And some of the people who study the laws of folding have examined how they generalize into higher dimensions.
With the opportunities of smart materials and folds that can be done on a microscopic level, is there nanotechnology evolving around origami?
Yes. The question is there nanotechnology evolving around origami? And there are several examples of it. The most nano and the by far coolest was work demonstrated about 4 years ago by Paul Rothman at Caltech. Since several other groups have picked it up, he's figured out ways of folding DNA. And there's a Nature cover that shows images of strands of DNA folded into like smiley faces and maps of North America. And now that's 1D folding, but he and his coworker and people who have joined that effort have now shown that you can fold the DNA into sheets and then have the sheets fold up. And obviously, you can't manipulate those with any physical object, so all the manipulation happens from chemical bonds pulling and tugging on things. But that's been done. On the not quite so nano level, there's quite a few groups working on making very small-scale structures that fold up. There's a group at Johns Hopkins that just had some work about a month ago on the cover of Applied Physics Letters, where they've developed liftoff technologies for creating patterns that will then spontaneously fold into both valleys and mountains to make highly patterned structures and surfaces. So it's quite an active area, quite outside the world of art origami. All right, well, thanks very much.